As this is a conference of web developers, let me start off with a story about my early beginnings in web development. In 2006, I started really diving into the web, and I built a website for someone else. I quickly learned about cross-browser concerns, like making sure a website worked consistently, regardless of whether you used Internet Explorer or Firefox. Yeah, Internet Explorer 6 was the most popular browser at that time. For the better, a lot changed since then. With Chrome coming out, many versions of Firefox, and a few too many of IE. I've learned my fair share of browser hacks and CSS tricks, and if I sat down almost 15 years later and tried to count them all, I'd be a mess. Fortunately, the human brain performs this wonderful trick. It forgets the things we haven't accessed in a long time that we know we don't need anymore, like how to do responsive layouts in IE6. Occasionally, though, I'll be developing for the modern web, and my brain will still recall some older technique that no longer applies. Some things stick, and it's hard to let go of them. JavaScript engines, it turns out, are just like our brains. Quirky and weird, they also have an amazing ability to forget. Like our brains, they forget based on what they believe is no longer needed. Like our brains, they don't always do this perfectly. Today we're going to explore how JavaScript manages memory, how it forgets, and what we need to do when it doesn't. I'm Will Klein, I'm from Longmont, Colorado, and I'm an engineer at Workday. I'm sharing this with you from my upstairs loft where I try to get work done while my wife and 3 small kids drop in about every 5 minutes because it's like I'm right here, there's no door. And with that, let's dive into memory leaks and the havoc they wreak. All my notes and links are available at willklein.co/memory. So the way that I learned about dealing with memory in JavaScript was on a project. We're going to take a similar approach today and look at some examples. So we notice our app is slow, or eventually it crashes the browser, and we need to figure out what's going on. Let's pull up our handy DevTools. Then let's check out that memory tab we've never really bothered to look at. First, there's this pretty cool section we want to look at showing our JavaScript VM instances. We have just one, and below that it shows us our total heap size, whatever that is. There's also a rate shown for how this heap grows and shrinks over the last 2 minutes. This right here can be really interesting. Your size is going to vary depending on the scope of what you're building. We can do more though. We can profile our memory. There are 3 options, but let's start with that first one and take a heap snapshot. Before we go crazy on this, what is a heap? Okay, while the heap is what we really care about, I need to introduce you to its best friend, the stack. The stack is neat, ordered. You just put things on top of it and take them off as you go. The stack needs to be clean. It's got important things to do, and it needs to be fast. It keeps track of where we are in our code execution. It knows what the current function is, what parameters it was called with, and what its local variables are. The current function call will be at the top of the stack, whatever called it will be underneath, whatever called that below that one, and so on. The heap, on the other hand, is a messy pile of junk. This, of course, is by design. For all of this to make sense, we need to consider why we need each to behave differently. Local variables are fine being stored along with their function calls in the stack when their values are primitives. These types are string, number, big int, boolean, undefined, and symbol. There's also null, but JavaScript gets really quirky on that one, and I'm not dealing with that drama right now. Then there's objects, which includes the traditional object, like an object literal, but also includes arrays, maps, sets, weak maps, and dates. The key difference of a primitive and an object can be thought of as how big can it get. Primitives are a plain, simple value that doesn't need a flexible amount of memory. You know how much memory you need for them as soon as you put them on the stack. No, you can put some objects on there too, if you're able to discern a fixed size and it's only needed within the function being called. Any other object can grow on the fly though. They're insane. You can add properties, grow the size of an array. It's like physics don't apply to them. If they live beyond that function call, we just throw them in a pile and hope they behave. They go in the heap. And yeah, that's how we end up with memory leaks. The only problem we get with the stack is that you can call too many functions without returning any of them. That's how we get a maximum call stack size exceeded error. Yeah, like a Stack Overflow. Everything else, the heap takes the fall. Normally it does work itself out though. JavaScript engines like V8 manage this memory space. They do garbage collection. For me, every Monday, a truck comes and picks stuff up that I don't need anymore. JavaScript has a trash collector too. This is Orinoco. When we're done with an object in our code, it will actually sit there for a short time while the garbage collector comes through and cleans it up. We're not going to go too crazy on this part, but here's a simple way to look at it. If the engine thinks another part of our code can get to that object, it keeps it. If it can guarantee it's impossible to get to anymore, it garbage collects it. The problem is, it needs to keep some of that garbage around when it's not sure. That is a memory leak. If you want to explore the relationship of the stack and heap further, Franziska Hinkleman has a great article on this. You should definitely check it out. Back to that snapshot. A heap snapshot is taking all that object data we talked about and grabbing a point-in-time view of everything. There's a lot here, so let's do something else that might be more useful. Let's interact with our application, click this button, and take another heap snapshot. Maybe we'll see something taking up a lot of memory, but usually we need to compare one snapshot to another. Looking at the state of the world before we interact with our app, then looking again after we do things will allow us to see what changes. Let's compare these snapshots. We can switch from viewing all objects on snapshot 2 to just looking at the objects allocated between snapshot 1 and snapshot 2. This will give us all the new things that were created when we click that button. I'm going to sort this by size, and we can see pretty quickly that there's a bunch of detached HTML nodes, 1,000 of them, that weren't there before. We can expand this and look at individual elements. We can even store them to a global variable, and this will log them out in a temp1 variable and a temp2 and so on, and we can see what they are. So we've got a list item, and we can debug from here and figure out where is this coming from. We can do things like look at its parent node. And then we see, oh, there's its UL. And that has a bunch of children, probably 1,000 of them. So from here we can start to debug, well, what are these nodes that are in our application? And we can start to think, all right, are they supposed to be here? Or are we dealing with something that we didn't expect? Another handy thing to do, especially if we don't have a giant obvious pile of detached elements, is we can filter for them and discover their existence even when there's only a few. Go into the class filter and filter on detached. Taking a step back, this snapshot difference is one of our best tools for auditing memory in our applications. Taking a snapshot at one point in time, interacting with the app, and then taking another snapshot, we can then use that comparison to look for anything unexpected or extreme in nature. From there, we can dive deeper and start to pinpoint the relevant code. In this example, we might recognize what UI components may be generating the detached list elements, or we might just search our code base for document.create element and see what comes up. Let's talk about closures. Here's a really interesting example. First, I'm going to show what happens in Firefox. Firefox has a really great visualization of the heap, and in this case, the increase in memory usage is really apparent across the snapshots. When we start off, we can see a bunch of different things: scripts, DOM nodes, objects, and strings. The strings is about to blow up though. As we progress through the timeline and sequence of snapshots, we see it basically take over the majority of the heap, eventually increasing tenfold in just a short while. The second thing to look over is the actual memory leak. To be completely honest, this one took a while for me to understand, and I'm still not comfortable explaining it. The key takeaway, though, is that closures can be one of the gnarliest causes of a memory leak. By their nature, they involve setting up a variable that's defined outside a function. It's available before, during, and after this function's invocation. It's possible that we refer to that variable within that function in a way that prevents garbage collection. This is a reproduction of an actual memory leak on the Meteor project. Credit to David Glasser for writing this up, and if you're up for a challenge, look at the original blog post. Let's go over some of the common patterns and pitfalls that can come up with memory leaks. Globals can be common, but with the right linting setup, we should only be creating them in an explicit way, like when we're intentionally putting things directly on window. Events and callbacks are very common, but the impact is usually small. It can still add up though whenever you create an event listener, Make sure you don't forget to remove it when it's no longer needed. I've got a fun example about this. Mistakes happen, and in this case, here's a pull request on an open source project that I found. There's a React component, and when the React component is added to the DOM, we have a lifecycle event fire, and we add some listeners so that way we can fire some callbacks when actions take place. Well, when it's taken out of the DOM and component will amount, that's when we should be removing modal listeners. This pull request fixed a bug where we're adding the listeners twice. I've done something like this before too. Third-party dependencies. I've seen trouble when not using third-party APIs correctly, especially when a resource of some kind is involved, like a socket connection or a queue subscription. Be careful to make sure you use the correct APIs to dispose of those resources. Caching. Caching is a big one. Definitely be careful implementing your own. Use a dependency whenever possible. If you need a cache, look at LRU caching, which translates to least recently used. Basically, the least recently used items are discarded. So if you care about the last 10 items, when you get to 11, the last one that was ever accessed gets discarded. Anytime you write code or use a dependency where set timeout or set interval are used, look out. Think animations or reconnect logic. Whenever you have time-oriented, asynchronous code like this, be careful leaning into other complexities, whether it's closures or third-party dependencies. Profile if you're not sure. Speaking of which, I'm a big fan of closures when they are needed. Just be mindful of when things get a little bit complex and consider profiling anytime you're not sure. Right now, there's a proposed browser API being tested in Chrome that promises to help us understand the actual memory footprint of web pages in production. Currently in Origin trial, it's available in Chrome 83, which came out in May, and is expected to be disabled later in November in Chrome 86. You can try it right now and see if you can gather useful info on how customers are actually using your applications. I only just learned about Origin trials, but it looks like you need to request a token for your Origin, add a meta tag to your HTML with a token, and then you can run a test in production, collecting data for any users using Chrome. Profiling on your local machine is one thing, but gaining insight of what happens with real usage is another. Using the API, it looks something like this. You want to check to make sure that you have the API available on performance.measureMemory, and then you can await it. It's an asynchronous call, and then you ideally want to take that result and send it to an API where you're collecting that data. I haven't done this yet myself, but it looks pretty interesting. The cool takeaway here for everyone is there's likely to be more improvements on how we measure memory in the browser going forward. I found the most excellent description that I think summarizes everything really well. I'm just going to read the words of Ulan, who works on V8 at Google. Browsers manage the memory of web pages automatically. Whenever a web page creates an object, the browser allocates a chunk of memory under the hood to store the object. The browser performs garbage collection to detect when an object is no longer needed, to free the underlying memory chunk. The detection is not perfect though, and it was proven that perfect detection is an impossible task. He goes on to say that there is a major discrepancy between when an object is actually needed and whether an object is reachable. JavaScript engines can only tell what is potentially reachable, and this will always include some things we will never actually need again. This might be because we did something wrong, but it also might be hard to foresee, as we saw with the closure example. And at the end of the day, we're talking about our app's usability for our end users. Whether something is too slow or completely frozen, it's going to affect someone trying to use what we built. That deserves our attention, and we should strive to deliver a stable and fast experience. To do so, we need to keep our tools sharp before we really need them. If there's one thing to take away, it's that. So when you get back to work, fire up your dev tools and take a heap snapshot. Watch your total heap size over the course of a day. Dive just a little bit deeper on how memory behaves in your app before it's a production issue. Pay attention to patterns and pitfalls we discussed, and over time, you'll develop an invaluable ability on any project. I really hope you learned something from this talk. Whether you're seeing this live or later on YouTube, please let me know how it helps you. And if you have any questions, I'd love to hear them. My email is will@willklein.co. My Twitter is @willklein_, and all my notes in this talk are available at willklein.co/memory. Thank you.
Yay! Thank you so much for that. That was great. I was thinking about making some kind of memory leak joke, but I wasn't sure if that would be too trashy.
Thanks.
Garbage collection, trash.
Oh, I get
Here all
it.
day, folks. But anyway, that was really awesome. I'm curious, what are one of the worst memory leaks that you've encountered in your projects?
Okay, so I was supporting a backend service in Node, and we didn't release code one week. We just didn't have anything to push out. So our service kept running longer than we expected. That seemed fine, except memory started increasing and we weren't sure why. And when we actually dug into it, it didn't matter the technical specifics, but we took a little bit, it took a few days to figure it out, and then it still took another week for the code to go out. And in the meantime, we had alerts going off, and we're running out of memory on processes that were running, and apps had to get paged, and they had to keep restarting the service. So it didn't feel good putting work on other people. So whether it's blocking our users from using the app, or if it's our ops people are having to support something that we kind of broke or we didn't expect, it never feels good when that happens. So we started more proactively checking our memory usage, whenever we made certain changes, to make sure that we didn't have that sort of thing happen.
Yeah, it's always tough when there's like people involved too, because you never know where lines might cross too. There was one time where I worked at a place where we had a memory leak, and it ended up affecting people's actual data, like someone's credit card info that they put in ended up being applied to the next user and stuff, and it was bad. Memory leaks are important to know how to fix. So in terms of just how you've dealt with them, and as you've had these experiences with memory leaks and how to deal with them and digging into them, have you had any aha moments and advice that you might want to share to people who haven't had those yet but might have to deal with them soon?
Yeah, absolutely. I think my first thing was the biggest thing I ran into when I got my first memory leak was I went and I started studying up on it and learning everything there is to know about memory leaks. Learned about garbage collection algorithms. Mark and sweep is one of them. It's and old space versus new space. I didn't talk about any of those things today, because when I actually got down to it, those things really didn't matter. Actually, just taking snapshots and inspecting memory and looking for what caused it, just debugging things and testing things and looking at snapshots was actually what mattered. So there's a lot of advanced things you can get into, and I encourage you, if you're curious. It's pretty interesting, but you really don't need to know all those really in-depth things to be effective.
That's awesome. Well, thank you so much again for your talk today, Will. I learned a lot, and I know that there were links flying all over the chat, so I really appreciate your time today.
Thanks, Cassidy.
And next we have Kelsey speaking, so let's go.